Sorry, my network went out. Let me be sure that it's recording. Yes. Yes, I'm back. Sorry. I saw your comment. Okay. Everybody can hear me now. Yes, sorry.
Yes.
The network just went out. Okay, I think it's
understandable.
Yeah. Okay, it's recording. Okay, we're going to continue. So the degree of freedom for chi-square is rho minus 1 times column minus 1, but not all chi-square. As you're going to see, for most Pearson chi-square, and not of, you're going to see not of form of chi-square. It's for chi-square that you represent by contingency table. And the final, yes, well, that's the logic, contingency table. Because though it's still the same principle, even the one you are doing restaurant with contingency table, you're going to see that you may just be the number of category minus 1. You're going to see it. Now, let's look at the degree of freedom for chi-square for test of goodness of fit. No, we are not going to be giving explanation of what, robust explanation on what chi-square for test of goodness of fit. So you can go and watch it. Once you watch this video, we have it. And for you that come for workshop also, but yeah, actually we have talked about it before on the lecture, series of lecture on chi-square. Yeah, in our video library on the net there. You get it through the website. Now, the goodness of it, all I just want us to know here is that you don't represent it, you don't calculate it by calculating, by having contingency table. The table you have is observe value, look at the table here, observe, expected. So all you need is the different categories of the outcome. Like in this example now, this one is talking of the block group, 4 block group, ABO, 4 block group, group A, group B, group AB, and group O. Those are the 4 categories. And the degree of freedom will be K, which is the number of categories, minus 1. You already know that for categorical variable, the degree of freedom is number of categories minus 1. So in this case now, for the test of goodness of it, this one look like a one sample t-test, where you are comparing your sample with a known population value. It's the same thing here. You are comparing what you have, the category you have, the proportion you have in the 4 categories. It's still the same number of categories for that, but the value, the percentage you have in your data set, you want to compare with the percentage in the population, theoretical one, which theoretical just means that the work has been done before. It has been published. It is believed that this is the block group for this population. Maybe for A is 63.3, for B is this, for this is this. So the percentages of the different block group are be given. So you are just comparing your own frequency with that expected frequency. Okay. In that case, there's nothing like cross tabulation of contingency. So there's nothing like row and column. Even though as you have seen this table, you can say there are row and column. There is not in contingency table. So the category are just along the row. So the degree of freedom is the number of categories. The category minus 1. So I think that one is clear. If you have your question, please type your question so that when we finish, we address. Now, let's look at the degree of freedom for McNemer and McNemer-Barker chi-square. So you can see this one also, though this one has contingency table, but it's another logic. Because in McNemer and McNemer-Barker, so it's actually the same thing. For McNemer, there are 2 categories of outcome of the you are dealing with. So and one thing with is for peer observation, that is before and after. So this is the counterpart of pair T, or repeated measure ANOVA. That is when you are dealing with quantitative pair before and after. So the categorical, here you use McNema and McNema-Barker. The difference between the two of them is that the McNema, there are two categories. McNema stroke McNema-Barker, there are more than two categories of alcohol. For example, now, if we are talking of hypertensive, yes or no, you did measurement of blood pressure for some people, you classify them as hypertensive, not hypertensive, two categories. You now do you prescribe exercise, you do many things. After a while, after some months, you measure their blood pressure again. You classify them into hypertensive and non-hypertensive. So it's the same group of people before and after. So because there are two outcomes, either hypertensive or not. So it's McNema, because when you cross-tabulate, what you do now is that along the row will be the before, along the column will be the after. But in McNema-Barker, that is McNema and McNema-Barker together, what happens is that you have more than two categories. Like for example now, example we use in our workshop was this socio-economic status before and after COVID-19. Imagine you get a group of Nigerians to measure their socio-economic class, you classify them into upper, middle, lower. So after COVID-19, effect of COVID-19, the same group of people, you came back to classify to see if there's any change. It's the same group of people. So the same three category, upper, middle, lower, before, that one will be along the road. Then the three categories, same three categories, upper, middle, and lower be along the column. So how do they meet? Okay, I think, okay, that one. So how do they meet? So the issue there is that the diagram we are seeing here just showing an example of how they move before and after. So what I just want to emphasize here, is that in McNema-Barker, the degree of freedom is not just row minus 1 times column minus 1. Each of them, they have pair. In the cell, they occur in pair. Look at this picture you are seeing now. Look at this picture you are seeing. You see, I give the color code. The pair of this picture, green. Okay, for people to really understand, I think there's a slide in under something I need to show. Let me just look for that slide and show you the one we treated under McNema and McNema-Barker. Let me just pick that slide and show you, because I think we need to pick that slide. Just a minute. I'll bring the slide out. Just a minute. Somebody asked question. Reserve your question till you finish. I just want to show us a slide, because it's like the slide I put there, you find difficult to understand. Where's that McNema-Barker? Chi-square, okay. I think it's under. Yes. Yeah. Yes. No, this is the other one. So the one I want to show is this one, so that you can get the illustration. Now, look at the example I gave you that time, socioeconomic status before and after COVID-19. This slide is showing. You see that along the diagonal is where, can you see socioeconomic status upper, middle, lower? That's before. After is along the horizontal, upper, middle, lower, along the horizontal also. The upper, middle, lower. Then you see Along the diagonal is, I put it white. Those are the ones that didn't change. Call it, those ones, they don't even get involved in the calculation of anything. They don't change. This is the number that were upper before and they were upper after. So they are not affected by anything. This 36 is the number of people that are middle before, they are still middle after. Can you see where they fall? These 93 are lower before and they are lower after. So they are always along the diagonal, the one that didn't change. The one that are off the diagonal are the one that change. The off the diagonal, can you see? This 7 here is telling you, or this 14 is telling me upper before, it become middle after. Why the opposite, which is the 7, they are painted the same color. There are people that are middle before, they become upper. Can you see? This one upper become middle, middle become upper. So those are they are pair. Those are the two pairs. The people that move from middle to upper and the people that move from upper to middle. Then the green are these 15, they were upper before, they became lower. And these 22, they were lower before, they became upper. So movement between upper and lower at this degree, they are pair. Even though they didn't touch one another, they are opposite. Even though they didn't touch one another, they are opposite. Now, the last one, the last pair is, look at this 57, middle before and lower after. And this 50, lower before and middle after. Can you see? So you see, this one is the movement between middle and lower. So each of the pair, you know, when you say something is pair, that is, there are two of them. So the degree of each of the pair has its own degree of freedom, and the degree of freedom is 2. Because when you say pair, there are 2 in number, minus 1. So what we are now saying, for each pair, the degree of freedom is 1. So if there are 3 pairs, the degree of freedom will be 3. That's for my, can you see that? For the simplest one, which is McNema, which is the simplest form anyway, you will notice that, wait a minute. The simplest form, this one, this is the simplest form. It's still the same thing, which is the McNema, without backup, because there are 2, this hypertensive yes, no, hypertensive yes, no, before and after. So there are 2 categories. That is the simplest form. There are 2 categories. And this diagonal, they don't change. This one is yes, yes. Yes, hypertensive before and hypertensive after. This one, no, no, no. No hypertensive before, no hypertensive after. And you see, these green, they are the one that discordant. So they are the change between no and no. This 52 was they were hypertensive before, they became no hypertensive after. While 32 they were not hypertensive before, they became no hypertensive after. So this pair, you may see that the table look like 2 by 2 contingency table. Yes, in 2 by 2 contingency table, the degree of freedom is 1 because it's number of row times minus 1 times number of column minus 1. You know, in 2 by 2 contingency table, the number of row is 2, the number of column is 2. So 2 minus 1 times 2 minus making 1. 1 times 1, 1. But the logic here is not the same. The logic here, there are only 1 pair. And that 1 pair, there are 2 of them. Minus 1, 2 cells. Just remove 1. The degree of freedom is 1. Though it's 1, but the logic is different from, it's not because of row minus 1 times column minus 1. It's just that there is 1 pair. And that pair, the number of degree of freedom will be equal to the number of pair. That is, there are 2 cells. The 2 cells minus 1. So that is what I was trying to explain with this larger one. So the degree of freedom depends on the number of pair. And the way we look at it, we show the number of pair. This one also, the slide was there before. Look at it. It's just a matter of, okay, look. Number of categories is K. That is number of categories. So if the number of cells, if you know it's K by K, the number, if there are 3 categories, you're going to have 3 rows, 3 columns. So it will be 3 times 3, 9 cells. So number of cells will be K times K. Like for this K category, it's going to be 9 cells. Then how many number of concordant, the one that along the diagonal, that doesn't change, is actually equal to the number of categories. Can you see? Number of concordant cells K, that is number of categories. That's what you saw in the other one. Just did. Can you see? Because there are 3 categories. The number of cells that are that are concordance are 3. The same thing, even the simplest from McNema. There are 2 categories. That's why there are 2 number of concordance. Then the only thing, okay, now number of concordance, discordant set. Number of discordant set, all you need to do is to remove the number of concordance from the total. When you remove, we will know that the total is K times K. When you now know that the number of the concordance is equal to the number of categories, just you remove that from the total, it gives you a number of discordant. And this number of discordant, they multiply by 2 because they are off the diagonal. They occur in pairs. So number of pairs of discordant will be half of it now. So if there are 12 discordant sets, it's going to be 6 pairs. So the number of that pair is going to be your number, your degree of freedom. If you calculate it, if you look at it, you see the answer here. The degree of freedom, can you see 136? That would be the number when you divide the number of discordant by 2, give you the number of pairs. Number of pairs is equal to the number of the degree of freedom. So in McNema Barker, degree of freedom is number of pairs of the discordant set. I think when you go through the material, you're able to understand it better. I think let me just remove this, stop sharing this slide. So okay, I see how. Okay, let's just continue. So I think I've given an explanation of that degree of freedom for McNema. Yeah. Now, degree of freedom for F distribution and ANOVA. No, F ratio is the statistic for ANOVA. That is, F ratio just means that you are dividing variance by variance. Variance among one variant by the other variant. That is F ratio. So in F, the F distribution is the pattern, the pattern of value, occurrence of the value of the F. Now, F is variance. Variance is the same thing as mean square. If you remember how you calculate variance, mean square deviation from the mean. Variance, how do you calculate variance? You say x minus x bar, that is minus the mean, which is deviation. When you square it, when you square that, it becomes square deviation. When you now sum it, it becomes sum of square deviation. When you now want to calculate the average, you divide by the degree of freedom. It gives you the average, which is the mean square deviation. You know, you have square it. So you can call variance mean square. So the variance, which is the mean square, when you divide one variant by the other one, that is the F ratio. Now, in what situation do you use it? Even though the F ratio mostly used for 2 things, as statistics for ANOVA, also to look at homogeneity of 2 variances. So it's just a division. When you say ratio, it's division. The word ratio means division of 2 things that have the same unit. So unit cancel out. You remember your physics. Ratio is what you get by dividing 2 quantities of the same unit. I usually give you this example. If you say 400 kilometers divided by 4 hours, it will give you 100 kilometers per hour. It's not just 100 because the kilometer that is the speed now. But if you say 400 kilometers over 4 kilometers, it will give you 100. It's not 100 kilometers because kilometer has cancelled kilometer. You are comparing 2 things. Both 400 and 4, they are kilometer distance. So you now say 400. I think this distance is more than the other one by 400 times. It's a ratio. Ratio has no unit. So when you say half of ratio, it means that you are dividing. Ratio is not about addition, multiplication, or subtraction. Ratio is about division. Dividing 2 quantities. So when you say F ratio, It means that you are dividing something. What are you dividing? You are dividing variances. So you can use F ratio to compare two variants if they are the same. That is to measure homogeneity of variance. Variance one, the variance of this group over the variance of the other group. Of course, if they are the same, it should give you one. If both of them have the same value, give it. If they are, for you, if they are not the same, they will give you anything other than have one, either less than one or greater than one, if they are not the same. So that's one aspect of use of F ratio. But this one, using it in ANOVA, means that you are comparing variances between and within. So I will not talk much about that. But what I just want to know, when we talk about, there are 2 degrees of freedom in variance, because we use variance, analysis of variance, ANOVA, whenever you are dealing with more than 2 means. So the underlying thing there is that there are 3 variances, level of variance you are dealing with, whenever you have 3 groups like that, or 4 groups. Total variance is the variance in the data set. All of them together, you can remove, you can calculate the mean, and remove the x from the mean, and mean from the each value, and square, and add and divide by the degree of freedom. It gives you the, so the degree of freedom in that sense for the total variance would be total sample over -1. The degree of freedom will be n minus 1, the total degree of freedom. But when we are talking of ANOVA here, there are other 2 variants apart from the total variance. The variance within each group, if there are 3 groups now, each of the group have its own total, has its own variance. And that is the one, you see, the variance within the group. Then the 3 group, I'm just using 3 as an example, they have different in between them. So the variance you calculate among the 3 groups is variance between groups. So dividing variance between group between group by within group is the F ratio. Now, what we just want to look at here is actually the degree of freedom aspect of it. Now, for 3 groups, between is going to be group minus 1. Look at the J minus 1. So the degree of freedom for the groups, for the between the variance, which is among the group, is the number of group minus 1. You will see that the degree of freedom is about number of entity minus 1. So in that case now, the numerator, the variance, and the variance for the numerator is number of group minus 1. The denominator, the variance could be for each of the 3 groups, n minus 1, that is n in each group minus 1. The sample size in each group minus 1. So that is why the ANOVA or F distribution have 2 variances. Can you see now? This one, look at this graph now. It's different from the one we're showing for T. Even chi-square, did I even show the graph for chi-square? Oh, I didn't show. Okay, I didn't just talk about it. The graph is there. Look at the graph. Depends on the degree of freedom also. No. Yes, this one. You will see T graph. You see the chi-square graph. It's only 1 degree of freedom. But here there are 2 degrees of freedom. You can see now D1, D2. There are 2 degrees of freedom. There is degree of freedom for the numerator. There is degree of freedom for the denominator. The numerator is for the group, that is within group degree of freedom. For the denominator is between, no, sorry. The numerator is between group degree of freedom. Denominator is within group degree of freedom. Those are the 2 degrees of freedom here. And just like T distribution, chi-square distribution, the F distribution, as the degree of freedom increases, the shape becomes, it look like normal distribution. All of them, as the degree of freedom increases. So What are the things that increase the degree of freedom for F distribution now? It will be sample size and the number of groups. You remember, the sample size now will affect the number in each group. It will affect the within degree of freedom. It will affect total degree of freedom. But the number of group is the one that determines the degree of freedom for the numerator. So the degree of freedom here now is a function of sample size and the number of group they have. While for t-test, it depends on the sample size alone. Then for chi-square, it depends on the category, the number of category or the variable involved. So it the category of the, so it will have, that is the number of the row and column in the contingency table. So you can now see that for F distribution or ANOVA, the degree of freedom depends on sample size and also number of groups. Now, lastly, let's look at the degree of freedom for regression. We are going to be, the workshop for this week will be correlation and linear regression. We have done workshop for ANOVA. You're going to see that ANOVA and regression, those people that have done workshop for ANOVA, if they come for the linear regression, they're going to see the ANOVA and linear regression, they are the same. They are two faces of the same coin. They're actually the same. Even from the discussion I want to make here, you have the clue that they are the same. Now, the regression model, in regression model, each term is an estimated parameter that uses 1 degree of freedom. Why I paint it blue, blue, blue? All these, the terms here now is talking about the number of predictors. Look at the equation for the first equation, simple regression equation. Y is equal to BO plus BS1 X B1 X1 plus error or residual. This you see is either you call it error or residual. Now, this is simple regression equation because there's only one explanatory variable, only one independent variable, which is this one. Of course, you know that the dependent variable is y, it's always 1. But the independent variable x, here is only 1 here. But multiple regression, this 1, 2, 3, and can be as many. It depends, it can be 2, can be 3, can be more than that. That's why we just put as many as possible, plus the residual. Now, for each, if there are the model aspect of it, the degree of freedom is divided into, just like ANOVA, the degree of freedom is divided into the degree of freedom for the numerator and denominator. When you add the two together, it equals the total degree of freedom. It's the same thing in regression. The degree of freedom is divided into the degree of freedom for the regression model and the degree of freedom for the residual. Now, I told you that this one, the regression and ANOVA, they are the same. What corresponds with the regression model here is the between in ANOVA, which is the numerator. What corresponds with the residual here is the within in ANOVA. So the degree of freedom between plus the degree of freedom within is equal to the total degree of freedom in ANOVA. It's the same thing, the degree of freedom for regression model and the degree of freedom for the residual equal to the total degree of freedom. Now, the regression, the degree of freedom there is the number of predictors there, which is, look at the K. Look at it here now. The degree of freedom for regression here is 1. The degree of freedom for regression is number. If there are 3 predictors here, it will be that. Now, you will see, look at the degree of freedom, total degree of freedom will be n minus 1. Just like in ANOVA, total degree of freedom, total sample size minus 1. But the regression model would then be number of the predictors. Number of predictor independent variable in the model is K. Will be the degree of freedom for each of them as 1, 1, 1. Then the residual degree of freedom will now be that total degree of freedom minus K and minus 1. This one is the number of the constant. The constant number, that is BO. So you see that the degree of freedom, the total degree of freedom will be N minus 1. For regression model is K, and for residual is N minus K minus 1. Okay. I think lastly, no, don't make me. Lastly, what is the importance of the degree of freedom? What is the importance? One, what are the importance? Computation of sample variance require computation of sample mean first. So if you want to calculate variance, you have to calculate mean. And in order for you to generate variance, you have to then divide to calculate variance mean square deviation from the mean. In calculating the mean square deviation, you don't divide by n, the sample size, you divide by the degree of freedom. That's one. So in calculating your variance, you use the degree of freedom. Then only n minus 1 score is sample are independent. Are free to vary. That is only n minus 1 score in a sample. Sorry, that's supposed to be in a. So only one n score in the sample are independent. Are free to vary. Yes. When calculating statistics like chi-square, T or F with hand, when you are not using computer, one need the degree of freedom to know if the value of the statistic is large enough to be statistically significant. So you have to go, and in those days when there was no computer, you have to calculate with hand, and you cannot calculate p-value. So what you do now, you now look at the statistical table and look at the corresponding degree of, because we know that most of these statistics, it depends on the degree of chi-square, as we have demonstrated. The chi-square, there are many distributions. B is a family-wise distribution. The shape depends on the degree of freedom. So there are different of them. The same thing with T, the same thing with F, we have just described. It's only standard normal distribution that is one that does not depend on the degree of freedom. So when you are doing statistics like chi-square, T-test, F, and over, in those days, you have to go and check the statistical table to check the corresponding degree of freedom before you can know the critical value. But thank God for the computer now. Gradually running, it will give you the p-value. So very soon, well, the only reference just made to the statistical table is for that, not for you to know if something significant or not now, because the computer will give you the p-value. So this is a critical value of chi-square. You will see for a 0.05, you can see that the critical value, this is the degree of freedom 1. The critical value is 3.84. You calculate chi-square now, if it's the degree of freedom 1, you have to first check if it is, this degree of freedom 1, the critical value is 3.84. So that is how you. Then if it is T-test, under, can you see under 0.05, this one, the third or fourth column, you see the degree, the value that corresponds to 1.96 is when the sample size is over 1,000, going to infinity. The 1.96, that is the critical value for standard normal distribution. So can it, the T distribution is like that. It's like a normal distribution when the degree of freedom is infinity over 1,000. That is when your sample size is over 1,000. So when you're having 1,000 now, look at the critical value. Of course, 1,000, the degree of freedom Okay, this 1,000 degree of freedom means 101, 101. Well, if it is two samples, maybe if each of them 500, 500, something like that. Now, the critical value for F, this F. Note, because that one has 2 degrees of freedom. So the numerator is along the row, the denominator is along the column. So for you to know the critical value, all you need to do is to know the degree of freedom for numerator and degree of freedom for denominator. So if there are 3 groups, the degree of freedom for numerator will be 2. If maybe each of the groups are 5, 5, 5, the degree of freedom for all of them will be 12, because each of them will be 5 minus 1, 5 minus 1, 5 minus 1. So to make it 4, 4, 4, make it 12. So now look where 12 cross 2. That value, 3.8, now will be the critical value for that particular. I think we stop here for question. I'm sure some people have questions. You have typed your question. Yes. Let me see the who have chatted question here. Okay. There's no question. No chats. Any question? Okay, let's ask. If you have question, you can voice your question out. Or if you don't want to ask, you can quickly chat.
Can I?
Go on, sir. Go on. Go on, sir.
Let me allow the people that have questions for this one first, because my question is for yesterday.
Okay.
So let me be the last to ask the question.
Okay, no problem, sir.
Let me be the last to ask
okay, no problem, sir. No problem. Okay, questions. Oh, that is very simple. That would be good. But things can be so simple that people have no question. You know, if you don't want to ask, that's what you can type. I will not say this is the person that has the question. There's no question that is stupid. So just ask your question. So we are here to learn. So that's why you can type your question privately to me. I'll just read the question out and answer it. I will not say this question was asked by so and so. So that's just it. Okay, no question. So you have to unmute yourself.
Okay.
Wait, sir. Many people may be talking.
Okay.
No, yeah. If you want to ask question, you have to unmute yourself. Because if you are talking and you don't unmute yourself, nobody will hear you. Because it's possible some people are talking and they are asking. We are not hearing. You have to unmute yourself first. Then you ask your question. Okay, if there's no more question, no question, Dr. Ikobo, you can ask your question.
Please permit me to share the screen. Permit me to share the screen.
Okay.
Permit me to share the screen.
I have done that.
Okay. This, yesterday, the sample size for the paired group was the last, and because of that, since it was the last, everybody was tired, and I believe that there are some areas that 1 or 2 persons don't understand. So can you see the screen?
Yes, I can see.
Can you see the screen?
I can see it, sir.
Okay. So this one is for McNema chi-square. McNema.
Yes.
Okay. Now, enter odds ratio to be detected. That one is clear. But under it, and the expected percentage of pair with discrepant observation. So these two have to go together. So how do you get the expected percentage of pair with discrepant observation?
That's what it's very simple. Most of the time, that if you still look at it, that is the minimum expected difference we talk about. That's the minimum expected difference. Minimum expected difference.
Okay, the same thing with the minimum expected difference.
Yes, now, it's a pair observation that is, if, let's say, it's 15%, maybe you are talking of people that have the Y, maybe there's an outcome you are measuring. Like maybe it may even be relapse, rate of relapse. no, cannot be relapse because we're talking of before and after. Maybe heal or not heal. I'm just trying to look for write something. So if, okay, you can even say hypertensive, not hypertensive, or anemic, not anemic. No, maybe some people you measure the rate of anemia before you say this person is anemic, not anemic. Later, you now come back to assess them. The percentage that is changed, if the average anemic rate of anemia was maybe 30, what is the 30%? What is the expected change? Maybe you want it to have changed by 10, you want it to have reduced based on your intervention. You want it to have reduced by 10%. That would be that. That is the difference you expect. So you want the average to be, you want the average, if it was 30, you want it to be 20 now. You want if the percentage of anemia was 30 before, among all of them, when you repeat, you want it to be 20. In that case, it's 10%. The change is 10%, 0.1.
So it means it's from your imagination. Because you have not carried out the study. You have not carried out the study. This is sample size now.
Wait, sir.
Sample size is the beginning.
We have already discussed this issue when we were talking about how do you get all those things you feed in? Because all those things, two things that are not constant, that are, well, most of the time are not constant, are this expected difference and the proportion you are dealing with. So all these other power criterion, significant criteria, they are constant. They are constant value. So when you do literature to check for the prevalence of something in previous study, that's this now. So sometimes in the previous study, they will tell you that this is the change you recorded in the literature. So you get it from literature, or you get it from experience, or you may not do pilot study if you cannot get one. You do pilot study to get it. Those are the things you get, yes.
Okay, it's
I think it's answer, right? Okay. You can stop here and it's like somebody send a message. Somebody send chat. What is post-op test when it is done? This way is asking the question. Maybe, okay, it's because Dr. Kobo brought what we did yesterday. In this person, you have to skip it. You have to do that one because I don't want to be discussing that. Because it's in your work. That's why you are asking. So I will explain to you. That's why you need to, maybe you should even subscribe first so that you get access to all the videos. So I will explain it to you. Post-hoc test is when you do ANOVA. Yes, when you are comparing, well, it's not only ANOVA, but it's commonly with ANOVA when you say post-hoc. You know, because ANOVA have to do with comparing mean between more than two groups. So when you do it, maybe you have three groups like your own now. We compare mean among three groups. And if the mean, there is a significant difference, where does it lie? Is it between A and B, or B and C, or A and B, A and C? So post-hoc test will show you where it lies. You either use post-hoc or you use plan contrast, plan comparison. So it's not only that one also. If it is you are doing Kukawali also, it's the same thing, because whenever you are comparing more than two groups, when you find a difference, where does the difference lie? So maybe somebody are asking you know, some people like academic, what they cannot do, they be asking question. Why I didn't run post-hoc test for your DC was because you have too many people. If you bring it as on me, you will be confused. Unless you want to put it. There is a post-hoc test you use to do the different in different, if you want to know that. Okay, we discuss that later. Don't confuse other people because they don't understand what they are asking. Then, okay, any other question? Any other question? Okay, I think it's well understood. That's why people, he said that is well understood, or people are confused, or people are not even interested because people are not asking me what we didn't discuss here. Though everybody has different interests. People come for different things. So I didn't hear any question about what we discussed. It's about what we did not discuss. It's okay. You can ask your question, even if it's not about what we discuss. You are free. Okay. Well, I've not sent out. Okay, let me pause recording now.